chipmunks. Quiet down, chipmunks. Please quiet down, thank you. Okay. Unit 3, Lesson 8, is about boundary value problems. So always before this, we've had dynamic systems modeled with initial value problems where we knew the value of the function and its derivative. However, mathematically, we might not always have that. So the demands of physical systems sometimes is that we need to solve a differential equation that has boundary conditions, and what that means is we know the values of the function or one or more of its derivatives, or even some linear combination of the function and its derivatives at 2 or more points, not at the same point. And several such examples follow. Here's one for the civil engineers: deflection of a beam. So many structures built by humans are constructed from girders or beams which deflect or distort, shall we say, they bend under their own weight or due to some external force. This deflection is governed by a linear fourth-order differential equation. And if this is our beam, see, if we hang the beam on this side and this side, then it bends in the middle a little bit. That's called deflection. So, and by the way, that deflection amount is our deflection curve, which is actually downward, is considered positive direction when you look at these. So, suppose the x-axis coincides with the axis of symmetry and the deflection is positive in a downward direction. In theory of elasticity, it is known that the bending moment, m of x, at a point x along the x-axis of the beam is related to the load per unit length, wx, by the differential equation. The second derivative of m, our bending moment, is equal to the load per unit of length, w of x. In addition, the bending moment, m of x, equals E times I times k, where E and I are constants, and k is the curvature of the elastic curve. E involves the elasticity of the beam's material. Steel is more rigid than lead, for example. And I is a moment of inertia of a cross-section of the beam about the neutral axis. This product, E times I, is called the flexural rigidity of the beam, and I promise not to call you on that one.
Very difficult.
Yeah, it's kind of hard. So anyway, you might remember this from calculus class. To find the curvature, it's the formula K is equal to y double prime over 1 plus y prime squared to the 3 power. And when that deflection is small, y prime approaches 0, so the denominator approaches 1. So the curvature is approximately equal to the second derivative. And that equation is used for curvature. Then, the bending moment is E times I times k, can be written bending moment is E times I times y double prime. But differentiating twice gives us the second derivative of the bending moment equals E times I times the fourth derivative of y with respect to k, which is like the second derivative of what we're using this as a curvature. And since w of x is that second derivative, recall, back to here, then we can write the fourth order differential equation w of x equals E times I times the fourth derivative of the function that represents the deflection of the beam. So, boundary conditions are associated with the equation, that's this equation. We usually wind up with boundary conditions depending on how the ends of the beams are supported.
Will this unit always be this complicated?
Well, yeah, it's kind of complicated, I gotta confess. So, what's called a cantilever beam is when you have a beam stuck straight out. For an embedded cantilever beam, the deflection y of x must satisfy two boundary conditions at the embedded end and two at the free end. One is y of 0 equals 0. Since there better not be any deflection here, it can't be. And y prime of 0 equals 0 since the deflection curve at the embedded end is tangent to the x-axis. Y double prime at L equals 0 since the bending moment at the end is 0. And y triple prime of L is 0 since the shear force at the end is 0, and you might have to look up shear force in your strength and materials book. So if the beam is simply hinged on a fixed end, then y of 0 equals 0, y double prime of 0 equals 0. So that gives us some initial conditions. If the beam is embedded at both ends, like this, there is no vertical deflection, and the line of deflection is horizontal at the endpoints, which gives the boundary conditions. Y of 0 is 0, y prime of 0 is 0, y of L is 0, see it doesn't bend at this end either, and the derivative is tangent to the x-axis. So here's a picture of that situation. So look at an example in the next video.
Ooh, this is fun.
Okay.